So, uh, two things happen when a wave moves. One, that we are defining a wave by its displacement. I mean, what's the displacement of this point, of this point, of this point? What's the displacement? This is this. Now, the displacement is dependent on two things. Which position are we talking about, and at what time we are talking about? So, if we take one position, then we will, like, this becomes SHM, because this particle is just going up and down, up and down, up and down. And then the equation is this. The equation is this. Uh, you can take this as Y. So in this again, we are, what is omega and then what is T? There are two factors here we are talking of. Omega is the angular frequency, is the angular frequency. What do you mean by that? It means that if I take the projection of this, if I put a shadow, if I put a light here, and if I see the shadow of this particle on, it will, when it's here, it will be here at the mean position. When it moves around with some angular speed, it will have go up and down, up and down. So this is the angular frequency. We are converting circular motion into oscillatory motion, into oscillatory motion. So if we want to see where if the particle is at the mean, it starts at t0 at the mean position, that means is zero. This is zero. But if it starts at time t with some angle, that means it is at some other location. It is not at the mean position. So this is called the initial phase, the initial state, and this is called the total state at some unit time. It includes the initial phase. So this is oscillatory motion equation. One particle going up and down, up and down. This is wave equation, which means that the how the wave is positioned at various times and at what position. The displacement depends on both. These are the displacement as a function of position and time. A is the amplitude. A is also the amplitude here. A is also the amplitude here. For one wave, in the oscillating particle amplitude and the wave amplitude will be same. And omega is the angular frequency and number. That means how this is. This is. I'll just tell you what the definition is. Omega is 2 pi by t time period, and wave number is 2 pi by lambda. So this is dependent on, this is a factor, it's called the propagation factor. And that this is dependent on the amplitude, the wavelength, and this is dependent on the time period. So these two things you should know. This wave is also, this is given here to this is also, this wave could be a rope. This wave equation is for a rope. It could be for water, any wave on water. It is also for EM waves. Now, the EM wave is a special type of wave. There are four laws in electromagnetism, and the four laws are these. There is a Gauss law for electricity. There is a Gauss law for magnetism. There's a Faraday's law, which you have done, and there's an Ampere. These four laws, if you simultaneously solve them, you will find that the light is just an electromagnetic wave. It is just an electromagnetic wave. What happens inside it? There's an electric field which is propagating, oscillating electric field, and a magnetic field. Now, this field, if you notice, if this is in the X, E is in the X uh, direction, B will be perpendicular to that, and it will be propagating in the Z direction. So they form a right hand rule. If you see, this is the same equation, kz minus omega t. He's taken the wave at time t0. It starts at 0, so that phi factor is missing. But that phi factor is missing. This factor he's not using. He's just using the simplified form of this. Now what happens? Just see what we are talking about. This equation. This is the equation, and E is the electric field, and here it will be the amplitude of the electric vector. The remaining is same, but in this case he's taking that it is moving in the z direction. It is moving in the z direction. So instead of x there, he's taking z here. And this, and B, the way B is also this same moving, but B is oscillating perpendicular to the z direction in the y, and E is oscillating in the uh, x direction. So they will be, all will be perpendicular. E will be perpendicular to B, and that will be perpendicular to the direction of propagation of the wave. It's like this, E cross B is equal to the wave direction. This you will do I cross J is equal to K, this vector product. This you will do in some place in maths. Acha, okay, now these are some relations, but the important thing is, why am I telling you all this? This is because we are going into polarization. Now, what is polarization? Once this wave goes and it hits water, it will reflect. And once it will reflect, it will cause a glare in your eyes. So sometimes you can't even see properly. I'll show you. And is that when an EM wave, a light, passes through uh, a polarizer. Now, the polarizer has some molecules arranged in some order. So there's a vertical slit. So there will be many directions which electric field is vibrating. Only one is allowed. Only one is allowed through the slit. The others are cut off. The others are cut off. So the only one polarized wave, the wave becomes polarized vertically, and wave vibrations are only in one plane. This is E vector. B is perpendicular to this, the magnetic field, and it is propagating in this direction. If you introduce another, so we got plane polarized light. This is E vectors in all. This has got glare, and once it passes, then its intensity reduces. And also, if you put another analyzer, we call it another polarizer, but it's called an analyzer. The If the molecular chains are perpendicular to this, no light will pass through. But if you put it at some angle, then some light will pass through, and that this way we can control the intensity by this law. If we have got unpolarized, first we pass it to perpendicular to this. That means if this angle becomes 90 degree, then no light will pass. And if this angle becomes 0 degree, that means the orientation of these and the orientation of these match, then it will remain as I1, I naught, because then cos square 0 is 1. Cos square 0 is 1, and the intensity. But if by controlling the angle, you can reduce the intensity. Now, polarizing can be done through passing it through polarizer. Polarizing can also be done if it hits the water. And if the angle of reflected and the refracted make 90 degree, then we get a very plain polarized light, and then you can see the details. The reflector is reduced when observed, so this allows to see the details. So it is also, so polarizing is done through one, polarizers and analyzer combination, two by water reflection, and three by scattering. Scattering is when light hits dust particles in the atmosphere, it scatters it and also polarizes it. So there are three ways you can polarize. Scattering of particles of light with dust particles, like polarizing when it reflects on the surface of water. Polarizer and analyzer. Okay. This is a phasor diagram. It's like a rotating vector, and the projection of that gives the displacement of the wave in the y-axis. So it's like we use in generating the wave of alternating currents, even in this is how the omega this omega, you see the phase difference. You can always visualize what's the phase difference by just imagining where this phasor is for one wave, and what's the other position, and then the angle between them. Okay. Acha. So this in this, if this is the phasor, so if it rotates once, it is 360 degree, and it will half, it is 180. So in this question, it has the if it was here first, initially it was here, so this was the position. Then it moved, rotated, it rotated 360 to come back to this position, and then it rotated, it came here, then it's got a projection of this. If it comes here to this, so it is 180, n means it is 360 plus 180, which is 3 times 180.